So let's start from early visual cortex. As I said, early visual cortex is particularly interested in things such as lines, edges, but also color and motion. And I should say, the lines and edges are particularly important because our brain really cares about where something starts and where something ends. That's one of the primary ways in which it segments the image, as we've seen earlier in this module, in order to understand what is inside, what is in a visual field. Now, I'd like to demonstrate this by showing a classic video from Hubel and Wiesel. Now, Hubel and Wiesel were studying visual cortex in cat. And what they did, the setup they had, which is what I'm going to show you, they would have a TV screen in front of a cat. They placed a recording electrode in the cat cortex, and then they would show a stimulus, typically a bar of light or different shapes. And by doing this, they would try to characterize different neurons inside that cat's cortex. Let me show you what I mean. And before starting the video, let me point out that although I will only show 3 snippets, in fact, an example of a simple cell, an example of a complex cell, and an example of a hypercomplex cell, you can find down here the link to the video so you can watch it in its entirety. So just to prepare you to what you're going to see, you will see the screen on which you will always see a bar or some kind of shape. This is the stimulus that is being shown to the cat. And then you will see one of the scientists writing on the paper, trying to understand what is the receptive field of the particular neuron they are recording from, meaning what is the type of stimulus that triggers activity in that particular neuron. And you will recognize that because you will hear a little sound that sounds like a crackle. Every time you hear that, that is the neuron triggering action potentials. Let me show you what I mean. So simple cortical cells to start. That. Bar turns on, that position, that neuron fires. It doesn't really fire when the bar is here, but before that position. It doesn't really fire when the bar is after that position. Fires when there's a bar that goes exactly through this part of the visual field. So that's what they're marking here. This is an area, this is the boundary to the right of the receptive field of the neuron, and now they're trying to find where is it that the neuron doesn't respond anymore above the area. Here it responds, but here or here it doesn't respond. Notice, it swabs the field in the wrong direction. If it has the wrong orientation, then the neuron doesn't. See, it's the wrong orientation, so that neuron does not respond. If you think of it, this is really reminiscent of those features that were shown on the feature matching theories, like the pandemonium model. It really looks like our early visual cortex owns the world with features such as lines and certain orientations, exactly the way that those feature matching models, the two-dimensional, portray. So that was a cell that responds to a line that has a specific orientation in the receptive field. Now let's look at a complex. See if you can guess what is the receptive field, what kind of stimulus this cell can. So these are the two side-to-side boundaries of the receptive field, the part of the field that this neuron responds to. Here, the right and the left. This is the lowermost boundary, and that's the uppermost boundary. See, this neuron seems to respond whether the stimulus goes right to left or left to right. In terms of its directionality, this neuron seems to like to be interested by something inside this rectangle, and it's particularly interested by motion side to side. Notice, once the motion becomes vertical, this neuron, the prior neuron was about finding a line in the visual field. This neuron is about motion within a certain area. And not only motion in an area, but a specific type of motion, right to left or left to right. You can elicit it pretty robustly also with anything in the field. Works very well side to side, but as soon as you change the orientation of the stimulus, it doesn't care anymore. That is a complex cell. Now let's look at a hypercomplex. You can hear it fire. So they found the upper and lower boundary of the receptive field. Now they're looking for the side to side. So that is the receptive field. So in this sense, it's not too different from the prior complex cell we've seen, except for the fact that, as you hear, it cares about motion from right to left, but not left to right. Look at this. It doesn't fire anymore. This cell only cares for stimuli that have this particular eye. It's a hypercomplex cell, this particular one. It responds to stimuli in that rectangle. It responds to motion right to left, not left to right, not up to down. And it only responds if the size of what it's finding is right. If it's too big, it stops responding. So see, this gives you a good understanding for what are the kind of features that early on in our visual system, our brain looks for. Remember, the retina really is just like a big field of dots. Each little dot is either on or off. Then that information through the thalamus reaches visual cortex, primary early visual cortex. And once it's in there, these kind of, you can see from this video, that simple, complex, and hypercomplex cells, they seem to reconstruct lines that have certain orientations, lines that move within certain quadrants of the visual field, and lines of certain directions, of certain sizes, that move in certain directions. So these are the features that our brain, much like the pandemonium model, looks for in the pattern that is sensed. Now, interestingly, even within early visual cortex, there appear to be some very important neural mechanisms that have to do with your perception beyond sensation. Look at this example, which is known as a Mach band. So look at this, rectangle here. You'll see that obviously it's light red on one side and it's dark red on the other side. Now, if you look carefully just nearby the boundary, you might notice that to the left of the boundary, there's a slightly brighter red, so lighter red line right to the left of the boundary. And conversely, just on the other side of the boundary, you might notice that there's an even darker red stripe right here. Turns out, not true. Neither of these two, the brighter red and the darker red little bands exist. They're purely a perceptual phenomenon, meaning that your brain makes you see them, but they're not really there. And you can easily see that just by covering one of the two sides with a piece of white paper. You will see that there actually is no such thing as this brighter line right here, which I see very clearly, and this darker line right here, which I'm guessing you two see very clearly. So this phenomenon, known as a Mach band, is a purely perceptual phenomenon. The aim of it is to help enhance the presence of an edge or the contrast of an edge. Now, the interesting aspect of this is that it's purely based on neural machinery. In fact, it's based on a phenomenon known as lateral inhibition. Let me show you what I mean. So let's say that we have a number of neurons, and we're going to arrange them side by side. Each of these neurons, all that they do is they see if right in front of them there is something or not. Okay, that's all that they know. Now, for the sake of this example, I'll put some numbers which will help explain how how lateral inhibition works and how Mach bands emerge from lateral inhibition. So what I'm marking up here is the actual intensity of the red, or rather the actual stimulation of each neuron. So each neuron receives stimulation proportional to how bright the red is. And these numbers are entirely made up. They just work well for the example. So let's say that these 4 neurons, which happen to be on the bright side of the band, they are receiving 10 worth of excitation. So each neuron is getting excited by the color 10. On the other hand, the 4 neurons that are on the other side of the band, so are quote unquote looking at the darker side of the band, they only get excited 6 by this particular color. So the real intensity out there is really just a straight line, very bright here and dark here. That's it. Okay. Now, let's add to this the phenomenon of lateral inhibition. Lateral inhibition means that every neuron, not only it receives excitation, but as it does so, it sends out inhibition laterally to its 2 neighbors. Okay. For the sake of the example, I'm going to assume that each neuron sends out excitation in proportion to how excited they are. Specifically, I'll say that they send out excitation of 20% of how excited they are. So if a neuron receives an excitation of 10, they send on each side an inhibition of 2. And again, completely made up numbers just to make the math easy on me and you. So let's take this neuron right here. It's receiving 10 of actual intensity, but it's also receiving a -2 inhibition from the neuron to its left, right here. And it's also receiving a -2 inhibition from the neuron to its right here. And also it's sending out inhibition to the 2 neurons. So these 3 neurons really, they each receive 10 excitation, but they also each receive inhibition of 2 from each side. So 2 from here, 2 from here. This neuron receives -2 from here, -2 from here. This neuron receives -2 from here, -2 from there. If you go to the other side of the band and you look at this neuron here, it receives an excitation of 6, but it's getting inhibited 20% of 6 from this neuron and 20% of 6 from this neuron. In other words, this neuron here is receiving 6 in excitation from the outside, but it's also receiving -1.2 inhibition from the neuron to its right and -1.2 inhibition from the neuron to its left. So if you put this together, the net excitation of each neuron is really the sum of these 2 numbers. So these three neurons really net, they're excited by 6 because they're excited 10 by the actual stimulus, but then they receive the lateral inhibition from their neighboring neurons, which dampens that excitation. So their net output is 6. If you go on the other side, exactly the same thing. So each neuron receives an excitation of 6 from the stimulus, really from the retina, or the thalamus rather, and receives an inhibition of minus 1.2 per side. So net, each of these neurons is excited 3.6. So this is for what happens on this side and what happens on this side. But let's look at the two middle neurons, which are the most interesting ones. See, this neuron here is receiving 10 excitation because it falls on the bright side of the band, and it's receiving minus 2 inhibition from the neuron to its left, and minus 1.2 inhibition from the neuron to its right, because the neuron to its right is receiving 6. It sends out 20% of that in neural inhibition. So this neuron is being inhibited 2 from the left and minus 1.2 from the right. So net, this neuron is excited 6.8. So this neuron is more excited than its neighbors because it's receiving less lateral inhibition from one of the two sides. So this neuron is more excited, is going to see brighter than these neurons. Hence, the little bright line that you see right here. Conversely, the neuron to the right of the border of this edge, it receives minus 1.2 from the neuron to its right in inhibition, and it receives minus 2 from the neuron to its left in inhibition. But because it's on the dark side, it's only excited 6 in the first place. So it's receiving minus 2 from this side, minus 1.2 from that side. So net, it's excited 2.8. Less than the neurons to its right, less than the other neurons in the dark side. Hence, this neuron sees this band as even darker than its neighbors to the right. And that's why, if you put these numbers together, the real intensity of this, the real intensity of the color on here is something like this: bright and then suddenly dark. But the perceived intensity, what you are perceiving, thanks to lateral inhibition in your primary visual cortex, is something more like this: bright, 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 even brighter, and then very dark, and then a little less dark. Okay. So lateral inhibition is a phenomenon, purely perceptual, that enhances the presence of edges. And it occurs thanks to a very specific type of neural circuit, which is lateral inhibition.